Good morning. Can you hear me?
Sir, shall we start, sir?
Yeah. So shall I begin?
Sir, wait, sir. Participants are there. We have a short introduction about you, sir. After that, you can start the session, sir.
Yeah.
With your
Sure.
permission.
A very pleasant morning to one and all present here. Dr. K. Sindhilkumaran is currently Assistant Professor in Indian Institute of Information Technology, Design and Manufacturing, IIITDM, Kanchipuram, Chennai. He is also the head of the Center for Smart Manufacturing at IITDM, Kanchipuram. He obtained his doctorate in Additive Manufacturing in the Mechanical Engineering Department of IIT Delhi. He previously worked as a guest researcher in the Systems Integration Division of National Institute of Standards and Technology, USA. His research interests are in additive and sustainable manufacturing. He is associate editor of ASTM Journal on Smart and Sustainable Manufacturing. He has been nominated for prestigious in-residence program for inspired teachers at Rashtrapati Bhavan during 2016. He has participated in various international conferences and published more than 30 international publications in peer-reviewed journals. As part of outreach activities, he is also the coordinator for Teaching Learning Center at IIITDM Kanchipuram, funded by MHRD India. He is also in charge of the design for the Additive Manufacturing Lab at IIITDM Kanchipuram, funded by MHRD India. We welcome you, sir.
Yeah. So thanks for the introduction. I think I welcome all the participants for this session. Hope all of you are able to see me. I'm not going to share my slides immediately. I'm going to share my slides a little later into this session, right? So hopefully, if you're not able to see slides, because I'm not sharing any slides as of now. So I'm going to introduce a few of the slides a little later. Okay, so I think I'm seeing a lot of participation, and many of the names that I see, mostly they must be faculty who have some teaching experience already, and some students, research students, and also few undergraduates or postgraduate students who are also joining this session. I welcome you, everyone. Okay, so and also I thank the organizers, Veerapan and from the Sri Krishna College of Engineering and Technology from Coimbatore. I think so they have taken a good topic for this particular program. Before I go into my session, I think all of you have some expectations from this program. When you joined, you wanted to learn something new. So I think many of you might be a practicing engineer already. So you're all problem solvers. You solve varieties of problems. So you solve varieties of problems. And in my opinion, so one of the things that we do at this point in time is we are looking at this particular workshop, which is titled as Environmental Sustainability. I think I work on both additive manufacturing as well as sustainable manufacturing. And when the organizers approached me, they didn't really reveal that it's going to be on sustainability. So because then I would have been really happy to be talking about sustainability angle a bit. But I think I took with the theme of the workshop being sustainability and that too environmental sustainability. So I have taken little care in arranging few of my talk around that area. So it will be more easy to connect, right? So okay, yeah. So I think the participants are free to stop at me at any point and asking me some intriguing questions that you want to find answer immediately, right? So I would be happy to answer questions on the way. Thank you all for joining the session. Okay, so sustainability is not a new term to many of you. And additive manufacturing is also not a new term for many of you, because you already have attended few sessions and many of you might be already making inroads into that area. And if you have not, additive manufacturing is about making things layer by layer from just a CAD model, and slicing the CAD model, you are able to make things layer by layer. So that's the only definition. So where you are making things one at a time, one layer at a time, and then you are building the three-dimensional object. Okay, so what is sustainability or sustainable manufacturing or environmental sustainability? Is basically utilizing resources in an effective way so that we don't harm the future needs or future needs of the generations, right? So good morning. I think in the morning WhatsApp we get a lot of good morning, and at night we get good evening. I would request participants to only message if there is any doubt. So I say good morning to everyone. So please don't type good morning messages. So it will be a little disturbing to others. Okay. So everybody will be focusing on the lecture. So good morning to good morning to one and all. Okay. So I'm happy to receive your greetings in the morning. Right. So yeah. So you can type in any queries or questions in the middle, so you can interrupt that. So please feel free to type any chat messages if you have any questions. Okay. But yeah. So sustainability is about, as I said, we go to library, right? So many of us have subscriptions in the library. Nowadays, the use of books have a little come down. But when you go to library, when you take a book from the library, we take a good care about the book. So we don't tear pages into it, or we don't use highlighter to highlight some pages, or probably we don't, underline some things or fold some pages or tear some pages, because we know for sure that someone is going to using the book after we return the book. So in the same way, sustainability is about that. So we borrow the planet from our parents. So they gave us in a particular way to us, and then when we return it to our kids, when we depart happily after we accomplished our task. So we want to make sure that we have not done any irreversible damage to the environment before we return our planet to the kids. So that is what the sustainability is all about. Sustainability is about sustaining human activity in the planet, generations after generations after generation. So when do we harm the capacity to sustain is when we cause some permanent damage to the ecological systems or the human needs. So human needs, I think, are multifaceted. If you look at hierarchy of needs, we have so many hierarchical needs. And human mind is also infinitely expanding, wanting more and doing more. They want to basically go to Mars, and they want to explore the universe, learn their origins, and save other planets and save other creatures on this planet, which is maybe endangered or maybe not so endangered. But trying to save the snails, trying to save the caterpillars, trying to save the bees. We also want to basically save the trees and also ourselves, right? So we want to save ourselves. And manufacturing is a wealth-creating activity, right? So when we do manufacturing, we convert raw material into finished goods, and then by the way, we make money. So that's good, because we need to have a livelihood. When you take a clay and then turn into pottery, put into a pottery wheel, you add value, you sell it, and then you generate income and you pay taxes, your country prospers. So manufacturing is a wealth-creating activity. That's the only definition that I understand. But in that process, do we really harm the environment is the question. So if you look at additive manufacturing is a new kid in the block. So why I say additive manufacturing is new, because we have been doing manufacturing for 3,000, 4,000 years. So from the day when we started using tools to the day when we started making fire, so the day when we started doing agriculture, So the day when we started using iron, bronze, tin, zinc, right? So, and then the steel age and the polymers, right? So we have been known to basically process materials and produce tools and goods for industrial use as well as for household uses, right? So, okay, what has changed over the years in manufacturing is so the manufacturing has become more centralized. So one country like China became the factory of the world, and everybody wanted to basically depend on China for their needs. So now in my room, if I'm sitting here, all the goods that I'm having in my room, all of them are manufactured in China. So everything that I have in my room, even the PET bottles, some of the bottles are manufactured in China, which I drink water from. So my mobile phones, my headphones, my UPS, my monitor, my telephone, my printer, my charger, my tapes, my punching machines, my stapler. So all of them are made in China. Even some of the chairs that I'm sitting. So the molds for them has come from there, the dies and molds. So it is a centralized situation. We've gone from craft production to mass production to centralized production, right? So additive manufacturing is trying to basically break that. So it is trying to basically break that. And it is trying to basically do reshoring. So now you see slowly China is becoming kind of self-sufficient, and other countries are trying to basically reshore some of their manufacturing that they have with China because they have differences of opinion, geopolitical reasons. And they also want to do friendshoring in other countries, right? So now additive manufacturing is being slightly moved to India because India is a friendly country compared to iPhone manufacturing has been slowly uh, reduced because of the zero COVID policy in China and stuff. So this is all about the geopolitics and other aspects of manufacturing and the background about additive manufacturing and sustainability, right? So now when you talk about technology wise, right? So I think we know that additive manufacturing produces components from 3D model data, right? So mostly it uses, and also it produces components layer by layer. And the world over, people have seen the conventional manufacturing techniques have produced a lot of waste. They are not energy efficient, and they are not material efficient. And they use large amounts of water and land. So it's not so sustainable, right? So for example, injection molding or die casting or sheet metal processing, or it could be something like machining or casting. So you use a lot of energy there. So now we are trying to basically see how additive manufacturing is more sustainable or not. Okay, so why this workshop is titled Environmental Sustainability? Because sustainability has three different bottom line. When I say bottom line is nothing but when you download a company's quarterly balance sheets. At the bottom of it is what you get is a profit. So the bottom line is mostly profit. So many companies, the bottommost line in their balance sheet is the profit that they get. So that's what they publish in their quarterly reports. So you buy a stock in Grow or Zerodha or any other app, then you study their metrics, profits over the last quarterly reports. So that's what the bottom line is. Now they added two more bottom line there. So that is called environmental and social angle. So we call, instead of profit, we also add people and planet. So triple P model is what is sustainability. So in the balance sheet, at the end of the balance sheet, you don't only count profit, but also see how much you contributed to the environmentally benign manufacturing. At the same right. So this is what we call as the triple bottom line. So meaning like we're not only interested in profit at the end of the accounts, so you also account for the energy, water, material use, and emissions in the accounting statement. So you also have corporate social responsibility. It is now being called as corporate sustainability reporting. or CSR, which contains all the things about industry, how they do and well and all, right? Okay, right. So now we are talking about environmental sustainability of additive manufacturing. As I already said, additive manufacturing is completely different from the conventional manufacturing. From the reason that you have some kind of what you call as this constructs. See, earlier it was mass production, now it is more mass customization. It was earlier centralized, now it is distributed. It is more, I would say, simple manufacturing products, now it is more complex products. So it is if you look at the supply chain,
Sir? Sir?
my connections.
Madam, it
I-
seems to be a network issue.
Yeah, so
Okay, sir.
my connection, is it okay now?
Yes, sir. Okay.
Yes.
Okay, great. Okay. Right. So now if you see, so a lot of people have thought about this in the past because, you know, our academic community is very vibrant. So normally any problems that industries create, we solve, right? So many times when you do, many times we solve industry relevant problems. We say industry relevant, but also industry created problems, right? So one of the problems that industry creates is pollution, emissions, right? So exploitation of the human labor in social angle, I'm saying. So it is not industry ready. We want to basically see also industry is also environmentally benign. So many academicians looked at from the industrial perspective, so industrial manufacturing, manufacturing industry as a whole, and try to ask this question about how sustainable they are. So trying to analyze them from scientific perspectives based on data, rather than beliefs and misconceptions and biases, right? So is there a scientific way, can I tell whether my process or additive manufacturing process is sustainable or not? That's a very big question, right? So can someone from the participants of this delegates of this workshop, would you be able to tell me a few tools that you know that can be used to analyze sustainability of a process or a product? Anyone from this? You can unmute and then tell, or you can type it on chatting window. So are you aware of any tools where I can select two processes and compare whether they are sustainable or not? Or I can select two products manufactured through two different routes and then compare. Are you aware of any tools? So you can unmute. You can be participating in this process. Okay. So if you are not aware, so there is a method called life cycle analysis. So it's a four-step procedure. It's ISO 14001-06 044 series.
Regarding optimization, you have asked something, sir.
Yeah, so I think my question is very specific. So what I was asking you is to name a method by which you can compare two processes for its environmental sustainability.
No, sir. We don't know, sir. I don't know. I don't know.
Yeah, okay. Tomorrow. Okay, so so the idea is like you can use LCA, life cycle assessment, or life cycle analysis as a tool. You can compare two processes, you can compare two products, you can compare meeting. So you can you can try, right? So you can try comparing that for many process, right? So if you look at life cycle analysis or life cycle assessment, it's the 4-step procedure, as I said. It is prescribed by International Standard Organization, so-called ISO 14,000 series, 14,001 to 44, right? So they have many different standards. So the first step is colon scope definition. Second step is you call them as what you call this life cycle inventory. And third step is life cycle impact assessment, and fourth step is interpretation. So, so the inventory is something like taking a process and analyzing its inputs and outputs, right? So how much, what is the energy input, what is the material input, what is the water input, and what are the emissions, like how much you get, air emissions, water emissions. Meticulously accounting them, just like you account for input output for anything. So it's like to take a system boundary. If you do it for the entire life cycle of a process or a product, so then it is called life cycle. So it's life cycle because you can do cradle to cradle, meaning from the raw material extraction to the transportation to the manufacturing, and then to the warehouse, and then the retailers, and to the distributors or consumers, right? So distributors and consumers, and then to the kabadi wala or the recyclers, right? So, or to the waste management or probably incineration plant and stuff like that. So essentially, you are analyzing the impacts of human activities on these materials, right? So when you convert them, when you transport them, when you manufacture them, when you sell them, so you can do a full-scale LCA from cradle to cradle, or you can actually put a boundary. So your system boundary can be drawn only to the manufacturing process, like additive manufacturing, and then compare between different processes. So that is typically called as LCA. Now, so what happens in LCA is like there are people who have done LCA additive manufacturing. They are available. You can just type in life cycle analysis of additive manufacturing. Will get many different peer-reviewed published journal articles and conference articles about it. So people have studied all the different additive manufacturing processes. Okay. Now, one of the things that they have done is, as I said, you have different inputs and outputs. So additive manufacturing uses materials in many forms. For example, I think you must have studied about the different ASTM classification. Your material extrusion uses filaments, right? So it uses filaments or wires. And in your powder bed fusion uses, and it can also use wire arc and stuff like that. So it uses varieties of different sources of energy. And the raw materials also varieties of different sources or forms of raw material, like powder form, and you use wire form and things like that. If you take material jetting, for example, it uses resins in the form of a liquid resin. If you take sheet lamination, it uses metal sheets or polymer sheets, right? So if you take binder jetting, it uses metal powders mostly, and also polymer powders, sometimes ceramic powders, right? So it's in powder form. And VAT photopolymerization uses material in the liquid form, right? So these are all different methods. So, but the problem is when they did compare different processes for environmental sustainability, you need to convert a material into these forms before it can be used. So they conveniently neglect sometimes. So you have a ore, you extract the ore, right? And then you form it to some ingots. And then the ingots go for some methods of, let's take a powder bed fusion, for example. In powder bed fusion, what happens is like you have different methods of making powders, right? So you use something like a water automation, and then you use gas automation, plasma rotating electrode, and centrifugal automation, and things like that. So you use varieties of such different methods to produce the powders, and each of them has certain levels of energy intensity. Energy intensity is something like for per kilogram of powder being produced, how much energy is being used. So if you see, for example, non-reactive materials can be processed through water automation. Reactive materials can be processed only through gas automation, like nickel, cobalt, iron, titanium, and aluminum. And then plasma automation is mainly for titanium. So if you want to use titanium powders in metal AN, you need to use these powder producing methods because you need powders of very small size, 50 microns average size, or 80 to 30 micron the powder size range. So you need to have something like 500 micron size or 50 micron size, and the specific energy consumption of this particular method. Specific energy is like how much energy I spend for per unit weight or per unit mass of that particular powder. So I can measure them in megajoules per kilogram. For example, you must be knowing that Ta64ALB is the most common material used in metal additive manufacturing, in powder bed fusion, in direct energy deposition, in band jetting, and all those processes, right? So even cold spraying, even electroaerodynamic injection, all those processes, people use titanium, even wire arc additive manufacturing too in some cases. So there they use the energy is something around 7 megajoules per kilogram. That's what the total energy that goes into producing the powder. So people conveniently forget this. So they forget this energy, and then they draw a boundary, and then they analyze the inputs and outputs for manufacturing process. And when they compare, let's say, another form for quite some time, because we have enormous amount of heat, that energy that is required to heat, maybe induction furnace, or maybe any other furnace that you use. It uses a lot of energy, right? So it's an energy intensive process. If you look at other materials, for example, even materials with a very high melting point, which is used in like nickel alloys, they have 14, for steel it is 1490 degrees centigrade. So nickel alloys still, it has still higher temperature of melt. So you need energy to raise the temperature to that level for a very large volume. So that means a large mass of this metals and then pour into cavity. If you draw boundaries properly, you can find the answer, whether it is environmentally sustainable or not. If I compare, let's say, 1 kg of a casting, 1 kg of a, maybe casting means like gravity casting or a die casting, and then 1 kg of machining, machined titanium parts, and 1 kg of, let's say, formed, something like a bulk forming process, right? So, and then 1 kg of parts processed through additive manufacturing, which one would have the lowest energy per kg? If you look at that, this question is really intriguing to answer. So you need to go into depth. You need to know where the material came from and what form they are available. For example, machine is not a primary process. For machining, you need a stock. That stock would have been first made into balloons and billets and ingots. You need rolling or forming, some other forming techniques to basically produce into that form. So you spend a lot of energy in the raw material extraction, from the ore to ore extraction to that ingot form. So that energy, if you again bring, and again, you see, directly using ingot to machining, whereas in here you need to use 7 megajoules per kilogram of energy to make it into powder form, and also store them in an air-conditioned room to avoid precipitation, right? So to avoid them, static electricity would be there. So, and avoid conglomeration of powders, storage requirements, transport requirements, and also additive manufacturing doesn't fully utilize all the powders, even though they claim in powder bed fusion you can take the remaining powders and reuse it. It's not going to result in a better objective. Okay. So if you look at it, overall, what I have told so far is about environmental sustainability. But today I'm going to talk about a study that we have done very recently. Okay, so I told about multiple processes, but we need to also look at, as I said, sustainability means not just environment, but also at the cost and economics is also very important. So I'm going to share my slides today. I'm going to talk a little bit about a hybrid, wherein you have both conventional, subtractive, and additive. We'll try to compare both and see which is having good material efficiency and stuff. So let me just share my screen. Okay, so just give me 1 second. Okay, so okay, so are you able to see my screen now?
Yes, sir.
Okay, just give me a second. Okay, thank you. Thanks for the confirmation. Okay, so are you able to see it in the full screen?
Yes, sir. Yes, sir.
Okay, so today I'm going to talk about a bit about hybrid additive manufacturing, which is combination of conventional machining and additive manufacturing. And what are the classifications? And I'm going to discuss a little bit about my literature survey that we have done for this study. And then I'm going to propose some kind of a strategies to maximize the material efficiency to increase environmental sustainability. And then also understand the economics of it with few case studies. Like this, I said, sustainability is more about triple bottom line, like cost and social and other angles. Right? Okay, so if you look at this, let's say you have a conventional process, right? So you have a pot like this. You take a large stock, and you have a tool. From the stock, you successively machine the material, and you waste some material as a chip, and you produce the final component. So this is CNC machining. It could be a 3-axis or a 5-axis or any other machining process. Now, the stock is what you bought. Okay. So here we are drawing the boundary very clearly. So you are buying a stock for a cost. So you are buying this large cylindrical stock and then machining it and getting this volume. So you are wasting a chip. Okay. And the second one is you are producing through a DED process. It's a nozzle where powder is delivered. Laser is centrally and powder powder. So you use a powder, and then you machine. Now opening here, 90% of the material as a cheap and weight issue has used in aerospace, which is to say that you bought a material. Let's say you bought 10 kgs of stock. Out of how many kgs aircraft that going to waste away as a chip, right? So that minus the original volume, that would be typically your part weight will go into the air. Normally call this as buy to. So if the buy to, that means you are wasting too much material. This is an example, right? So you are using tool to successfully machine final shape. You are wasting kg of material. Part per kg, you bought titanium material, TAC 4A, and you know that extremely expensive. And this is the stock that you produce through AM and finally finish machine it. So you waste only, let's say, very small amount of material compared to this as a waste. So that is what is hybrid additive manufacturing. In hybrid additive manufacturing, you take a part and then slightly enlarge by giving a machining allowance and make it in AM and then remove that delta volume that you added for machining or machining allowance, and you waste little amount of material of very expensive material. So this has been an approach that has been proposed to save material. But we will examine this hypothesis. We will take some real world case studies and other approaches to basically how we can approach this hybrid additive manufacturing, and also economics of this to understand the environmental sustainability angle as well as the economic sustainability angle. Okay. Okay, so some potential benefits of hybrid additive manufacturing. You must be knowing that today the world is moving towards making very large components in AM, not even just additive manufacturing. We are trying to build an entire house, entire bridge, entire rocket. Um, so it's not toys anymore, right? So they are making real world objects. So this is the nozzle which is used in the rocket engine. And this is the fan case and turbine housing. These are real world parts. They are very large parts and they are made of expensive materials. And there are commercial machines. There are more than 15, 16 machines available today, which can do both additive and subtractive things in a one single workstation. So you can see this is the one example of a commercial machine called Laser Tech 65, and it's a DMG Mori machine. It has a nozzle, DED nozzle, which has a powder feeder, and the laser which comes in from the center. And then you produce one feature, right? And then machine it, and then build another feature in deposition, machining and deposition. And then finally produce a component like this. So you can see you can build off-axis components without any support structures. It is a multi-axis deposition system where you can in multiple axes. Earlier 3D printing, you slice them in only one direction, you build the entire part in one direction. But here you slice them in multiple directions, in multiple axes, and you can reorient them and build in different directions as you want. Okay. So that's the idea of DED process. Okay, so if you see the way they achieve this hybridization may depend upon what kind of process they are hybridizing. They can take a 3D welding torch, like a normal welding torch, with a cold metal transfer technology and milling machine together. So it becomes the metal deposition model. The delivery is deposition model. You can actually have a welding torch. Metal wires can be passed on. You can use a plasma deposition, still use the powder and the energy of the plasma. So that way, it again becomes a DED machine and then it becomes hybridized. Also do micro casting, milling plus sharp peening. So again, this is a hybridized process where you do a little bit of casting and then milling. Sharp peening, which is also typically called this, a hybridized process. But here, you see you are using plasma as an energy source, plasma arc. If you use solid state fusion, so you can use ultrasonic welding plus milling, then this process is sheet lamination, and then you use a sheet stock. If you use layered compaction manufacturing plus sintering plus milling, then it is a PBF based hybridization. You can mostly for ceramics that people use this type of method, right? So if it's a DED base, which is typically laser based AM, so laser based laser deposition and plus milling. So which is a DED process here. This is the one process that I actually we have chosen for this work, which we are going to present today. So also you can use powder bed fusion, where you can use laser sintering plus milling, right? So it's like things like that. Okay, so so I think are you here? Any questions until this point? Is there any questions? Okay, so let me just go back to the slides if there are no questions. Okay, so yeah. Now, if you look at the literature, so there are a lot of literature that we wanted to focus on the material efficiency or buy-to-fly ratio. There are some researchers who have focused their attention, especially titanium, like because it's an expensive material. So Datta actually he has discussed about material efficiency, but mostly in a single AM process, not with hybridized process. And Liu talked about the need for hybridization, but he has not even looked at, but he discussed a lot about material efficiency in his work. So this particular researcher, Hodonu, so he did a material design process selection. He discussed the importance of buy-to-fly ratio, especially in selecting a material form rather than analyzing it. And also looking at a basis for comparing different processes, the cost, because at the end of the day, people want to basically make profit. So we wanted to basically use cost as a basis to decide to go to the extent of how much additive and how much DED that we should do, right? So that's the very important contribution of this one. So for that, we introduced few cost models, which I'm going to show you, and we reviewed few cost models from the literature, which talked about estimating cost of manufacturing process through AI. Right? So these are some mathematical models that were available at different points in time. Different researchers have done such a study. And these are some cost model studies, like so especially they were talking about how to reduce the cost by reorienting the optimizing the process parameters, and then modifying the design, or reorienting the part, or probably placing the parts together, or combining part consolidating the parts together and stuff like that. So these are some cost models which were available for different methods. One is sintering, and another is beam melting through electron beam, and mass projection and material jetting. So lots of such studies are there. So in this work, that the main objective that we wanted to do is to identify how much. So when you are hybridizing conventional and additive, one important question that we must answer is how much volume that we can do as additive and how much volume we want to do as AM. So let me just talk about a very complex part. So there are some parts which has a higher complexity, which is ideal candidate for AM, and some parts which are simple, which can be produced through machining. See, I have been giving a lot of talks in the past. Many of you might have even heard about my talks, where I always talk about cost versus complexity angle. So the more the complexity in the conventional manufacturing process, the cost is going to be higher because of the tool accessibility issues, work holding challenges, multiple setups, increased machining time, and sophisticated technologies like 5-axis machining and stuff like that. So simple parts are relatively cheaper to make in conventional manufacturing. It could be even machining, injection molding, die casting, forming, everywhere. So you must have seen there's a book called Design for Manufacturability Handbook by James G. Bralla. 1,500 pages of textbook only talking about what shapes you cannot manufacturing in conventional manufacturing, while additive manufacturing kind of makes design freedom available to designers. So it eliminates all these design constraints because you're solving a three-dimensional problem in a 2D way, like you're slicing them and making layer by layer. So anyway, you're breaking down the three-dimensional complexity into one-dimensional complexity. So now we are juxtaposed to design about what volume of that part which I should make it in AM and SM. So hereafter I will use this term AM for additive manufacturing, which is especially the DED process which I am referring right in my example that I taken for this study. And SM means conventional milling machine, right? So conventional milling. It could be CNC milling, but I'm not saying it's a manual, it's any automated manual, whatever it could be. SM means I'm talking about subtractive manufacturing. AM means additive manufacturing. So when I say SM means like milling. AM means I'm referring to something like a DED process. I'm hybridizing both milling and DED, laser-based process. So that's the objective. Let's now look at these two case studies which I just explained. So you take this example of a part. You have relatively simple cylindrical part. It's ideal for lathe, right? So you can take a cylindrical stock, put into a lathe, right? And then machine the inner an outer surface. But when it comes to building or machining this complex blades, shaped blades, the freeform machining, it takes a lot of challenges because thin wall, you need to have a, so it's if the workpiece is flexible and the tool is flexible, so you have this flexible, rigid tool, flexible workpiece, flexible tool, rigid workpiece, flexible workpiece, flexible tool, rigid workpiece, rigid tool. So these combination problems we encounter, leading to a lot of errors in machining, so tolerance issues and stuff like that. So, and also accessibility of the tool, right? So tool has to reach, and you need a fire machine to basically plan the tool path and avoid collisions on the machine, the zone with the tool and stuff. So it's really challenging, holding the workpiece and maintaining the datum and dimensions and geometric tolerances for the mating condition, because they are all going to be assembled into a shaft. So it's a challenging thing, right? So the moment when somebody throws a part like this to you, so additive manufacturing can kind of make this blades, which is very easy, can slice them and make them very easily. So for them, it's like very simple. For machining, it could be really complex. So I could split this part where I could make these features, which is, let's say, make it in subtractive manufacturing. And this feature, I can make it in additive manufacturing. So, but the thing is, how do I decide? How do I tell this? Because I had my brain, I applied my mind. So I looked at the part and said, this is really complex for me. And I understand because I have my knowledge. So right now in my lab, we have developed fairly good amount of vision support system, which can take a part as an input without any human input. It can detect the complexity and decide which is good for A, which is not good for A. We have developed 5-level metrics at the feature level, at the part level, at the assembly level, at the product system level, to analyze any design and say which is complex, which is not so complex for A. So we have done that meticulously using V-Similarity, and that's a different publication that we had. It's another 3-4 PhDs that we have guided. We have been guiding to, right? So that's a different. I will talk about that in the future, right? So when I get opportunity to talk about understanding complexity of design. But here, from my looking at this part, I think fairly with a good knowledge in manufacturing, people who had a workshop, they could tell that these are the problematic features for machining, and this is a very easy part for machining. And then you take the problematic complex designs to AM, where it becomes so simple and economical to make it, whereas this is more economical to make in SM, not in AM, right? So that's why this is one way of splitting. We call this as feature-based volume partitioning. This is the second method, which is typically what normally people have been doing for quite a long time, which is you have an actual part, right? So since you are trying to basically reduce the buy to fly ratio to avoid taking a large stock and then taking only 10% of the total volume inside. So I can just add a small 15 to 10% additional stock material around the part and get a near net shape part built in AM and then machine it. So this I call this a stock based near net shaping volume partitioning method. So in this talk, what I'm going to do, I'm going to compare these two different methods. So the method one, where I'm going to compare the feature-based volume partitioning, and second one is stock-based near-net shape volume partitioning. So these are the two things which I'm going to compare. So before that, I want to build my cost model. So for laser metal deposition, so how do I estimate my total cost for additive manufacturing, which will depend upon my pre-processing, as I said, about how much time I need to wait before the part gets heated, and also data preparation time, and also time for preparing the things like that. So processing time, and we need a lot of post-processing, like support removals in some cases, heat treatment in some cases, hot isostatic pressing in binder jetting, something. But DED doesn't. This model is for DED. So we have built a meticulously all this pre-processing time, processing time, post-processing time, and in processing time consists of deposition time and rapid motion times. And then we build the total cost model. This is the manufacturing cost model. The previous one, which you saw, is a time model. From the time model, you can get the cost model. The cost model is like, what is the total cost of manufacturing this? So what could be the machine operation time, labor cost, labor time, material cost? So this gives you an idea about what is the total manufacturing cost. And then we built the model for the machining. So this consists of setup time and machining time, and also changeover times, and also you have reorientation times and stuff like that. So tool change times and things like that. So if you take the total time, the machining time would involve cutting time plus rapid motion time. So that would be the time model for the CNC machining. And this will be the total manufacturing cost for machining, or SM, we call subtractive manufacturing, which is typically involves cost of the machine operation cost and labor cost and material cost, right? So, but you see, when we study material efficiency, we'll be more interested in this material aspect. So this MEA is typically called material costs. We'll be more focused on material because we are looking at material as one important efficiency, as one important sustainability. environmental sustainability factor, because materials are scarce. If you can save some material, if it's more efficient, you are environmentally sustainable, because you spend a lot of energy to produce material. If you waste material, you also waste a lot of embedded energy with the material, right? So that's the idea. So we have done the models for time for both machining and additive manufacturing, SM and AM, also cost for SM and AM. Then if you combine them both, that is the laser metal deposition plus CNC machining, the so-called hybrid additive manufacturing. And if you look at the total time, considering the feature-based volume partitioning method, it would be the individual time of additive features plus individual times of subtractive feature, SM features and AM features, add them together. And so you just add these things together. And then once you add these things together, you kind of, totally there are 10 AM features and 10 subtractive features. Add their times and add their cost. So this is the time model. This is the cost model. Okay, so, and this is the hybrid additive manufacturing, whereas additive time plus subtractive time, where manufacturing time in AM, manufacturing time is something you have already found out, you just add them for hybridization. So this is for a stock-based method. In stock-based method, so we also have cost for hybrid, which is typically coming from addition of the cost for additive manufacturing and cost for subtractive manufacturing, so which you have founded from the cost models of AM and SM separately. And if you add them together, you get the hybrid cost, right? So now, so I'm going to basically compare two different case studies today. One is a turbine blade, and one is an impeller model. And these have a bounding box volume of this. And the material that I have chosen initially is inconel, because we want to basically study the nickel-based alloys, which is also an aerospace material. And the mass of these two parts, the first part had a mass of 3 kilograms, and this one has a 21 kilogram, and the height is relatively higher here. That means it has a good aspect ratio, and this is not having such a very high aspect ratio. So the volume ratio is also defined, which is the volume of the part to the bounding box volume, which is going to tell us a lot about bite-to-fly ratio, because your stocks will be the bounding box. And if your volume is so less than the bounding box, then your bite-to-fly ratio is going to be very high. That means the impeller will have the poor bite-to-fly ratio, which is ideally good case for near-net shape, stock-based near-net shape feature partitioning. So this is the good case for feature-based near-net shape. You can make a conclusion, but still we have to further study about their cost models and time models, and then we'll make a decision. And we assume these process parameters for this LMD process. The power of the laser is around 750 to 850 watts, and the speed at deposition is 3 to 5 mm per second. And the powder feed is typically happening at 6 to 12 grams per minute. And we use carrier gas to basically shield and carry and shield. So that is typically 240 to 480 liters per hour. And the nozzle usually stands at a distance. It increases the catchment efficiency. So for example, there is a very important term called catchment efficiency. Catchment efficiency is like you have at a particular instance so much of powder flowing into the work zone. Only a fraction of that gets absorbed into the metal, and the rest of them can be reused, but still some of the powders that gets into the melting zone, while actually it melts on the fly. So whatever material that goes into that is actually divided by the total material supply is given by the catchment ratio or catchment efficiency. So that will depend upon the stand-up distance, and you have we assumed a catchment efficiency of a very low value for some process parameters and very high value for some process parameters. So you can just look at this. It varies largely from 10 to 17%. It depends upon many factors like the orientation of the surface with respect to the vertical direction, nozzle orientation, the substrate orientation, so many factors. So in fact, we have recently published a paper entirely on catchment efficiency, optimizing for thin wall deposition using LMD. So that's a separate work. Maybe in some other talk we'll talk about it. So this is the time and cost estimation assumptions. So this is the pre-processing time, and this is the cost-related data for what is the machine hour rate for LMD, and what is the machine hour rate for CNC, and what is the electric discharge machine hour rate and stuff like this. We have what is the cost of material which is available in powder. Using powder is expensive than the stock like ingots, which is used for machining. So even the buy to fly ratio we can compare, but still you see when you're using powders, it's slightly expensive because you are at production of the powder away, from your boundary, system boundary. Okay, so these are the two case studies I talked about. One is basically a turbine blade, and another one is an impeller. So you can see how the partitioning of these two will affect, right? So in subtractive machining, if I compare the total cost, so if you see it's like 1044, which is typically minutes. So here you see it's like 7,702 minutes. So it means like turbine blade takes very less time in machining, whereas impeller takes a lot of time in machining. So if you look at the cost wise, sorry, this is the total cost, this is the time. I'm sorry, 451 minutes is the time, and 3,100 minutes is the time. And this is the $1,000 is the cost, and $7,000 is the cost for impeller. So this is the cost of subtractively manufacturing a turbine blade, $1,000. And this is the cost, $7,000 is the cost for impeller. One impeller costs this much to make it in subtractive manufacturing, considering bulk of them is material. Okay, so now, so we'll just go with the feature-based volume partitioning approach initially, and we'll study. Then we'll go to the volume-based partitioning later. So I'm going to basically choose this as some subtractive manufacturing, only the complex blade profile. I'm going to use it as a AM feature. So this is the way I'm splitting. It's my assumption that I'm not using any partition support system at this point in time, but actually this is a little older work. Recently, we have made addition support system, which itself can suggest us like what volumes are really good for AM, what volumes are not so really good for AM. Okay, they do not take into cost and time aspect that I'm studying here, but they purely look at it from a human's perspective. So it's like, you take object and then you view them from different directions. You tell them how complex they are. So it looks like that. So we have built an AI system which takes images of the object at multiple angles and then compares the similarity of them using structural similarity analysis, and then tells us how much complex these features are, and then selects it for a base candidate for selectivity AM or SM, right? So in this case, these are the complex parts. The hub is typically a subtractive manufacturing feature, and the splitters and blades are additive manufacturing features. So we are trying to compare the time for a feature-based volume partitioning. If you look at the feature-based volume partitioning for the hybrid additive manufacturing, so this is the total time in AM. So turbine blade takes 108 minutes, and impeller takes 300 minutes. And this is the total time for subtractive machining. So it takes 200 minutes and it takes 11 minutes. If you look at hybrid additive manufacturing, it takes 300 minutes and 310 minutes. Almost, you see, total time in hybrid is almost closer. So compared to the previous only SM, you see it has drastically come down. The total time was something around 700 hours, right? So you can see that the total time has drastically come down, increased material efficiency, right? So this is the cost of it. You can see we had $7,000 at one time. Now it's like it has gone down to $1,200. It was around $1,000. Now it has become off. It has become 1/7 using the feature-based volume partitioning method. So that means it works for reducing the cost of the total build time is also getting reduced. The total cost is also getting reduced. Okay, what about material efficiency? We'll see that a little later. Okay, so we'll come to that part. So now we'll look at the second case. So this is the second partitioning strategy. The first partitioning is a feature-based one. Here, as I said, in stock-based BNF shaping, this is the entire geometry, right? So what we have done is we have added, this is the gray one you see here, or the maroon color, or I'll say the brown one that you see here is the actual part geometry, which is to be produced in CNC, but we have added 15% stock to it for subtractive machining, subtractive manufacturing. So that 15% stock is into the, plus the actual part volume should be built in AM as a stock material. This stock will be taken to machine to remove all the other materials. Like that, only 15% material is a machining allowance that has been provided. Very similarly, here you have a turbine blade. For the entire geometry, we produce 15% stock. We made that in AM, build layer by layer. This is the way maybe you will be building this part, or maybe inverted way, right? So you build this part in a DED machine with the 15% stock added, right? So then we will see how fab how does that work? So if you see here, the time has not reduced comparatively for the impeller part, but in turbine blade it reduced considerably in the stock-based method. And the cost is slightly higher here. You can see it goes up to 2,000, whereas but the cost for turbine blade is working fine. So that means for some parts, it's giving a lot of good comparable results to feature-based, but in some cases, it doesn't give comparable results to stock-based. So this is the, again, comparison of cost. It slightly went up. You can see that the cost is fairly same because the total cost in additive manufacturing is around $344 and to $3,000, and only machining is, like you see, it has drastically reduced the machining cost. So earlier you would have seen the machining cost was extremely high, 7,000. It has come, the machining cost, from $7,000 to $200, not even $200. In fact, $1,020, $120. So where is $7,700 and $120? So it has reduced, but it's slightly added to $3,000, $2,200 for the stock building, right? So anyway, you will be incurring some cost for buying stock. When you are buying stock made of AM, or when you are making a stock made of AM and then machining it, so you see you have reduced the total material cost equation, almost negligible, right? So which is lost as a change. Now, this gives a lot of good insights about what happens in the environmental sustainability and other aspects. So if you see, so which type of cost is most influencing? Is it material or operational? That we wanted to basically understand, because we are looking at material efficiency or sustainability from the angle of sustainability. We wanted to basically understand how much of this total cost is coming from the material and how much material savings is being done just because we are doing this hybridization. That's what is the question. Because we are saving money, that's really visible now. We could see that the saving money is very clearly visible. Time is very visible. We are having quite a good productivity, quite a good cost savings profit. But are we really good with respect to environment? Are we saving enough material? That's what we want to basically understand. You see, this is the material cost. So this is the labor cost. So you see that the labor cost is very, very less in sustainable, in conventional manufacturing, or small steel manufacturing, but the match extremely high compared to $1,000 we had, right? So for that turbine blade, this is the turbine blade, this is the impeller. So it's 50%, almost 40 to 60 ratio. But use stock-based, the material actually is much improved. Means the buy ratio is extremely good when you have hybrid manufacturing using stock-based approach rather than feature-based approach, because you will still have lots of material costs that you have to incur. So I'm not saying cost reduced means efficiency is improved, but as a proxy. But we'll see actual efficiency values too, right? So after a little while. Now you have this 156. Can you see this 156 much lower? Very similarly, you see that feature-based thing didn't really improve the material portion, even though the total amount is, let's say, for example, the total amount was somewhere around $7,000. It has been reduced to $1,000, but the proportion of the cost, even though it is like I'm trying to compare in percentages. That's why you are seeing these are same, but they are not same. If you add them together, it would be coming somewhere around $1,200. But this will be some dollars. We have just, but that still the proportion of the cost is something like $1,000. Even though this is 4 times lesser than the material cost of this particular aspect. So you can see that way you can compare. Like, so like you can see that the majority of the cost is only material cost. Operational cost, it gets reduced in HAM out of the total cost. But still, if you compare with SM, it's larger improvements is possible. And stock-based nearly have done the material, but still than that. But out of the total, the proportion material cost is much lower. That's what we want to hear. So this is the first subtracting, and then hybrid AM based on feature-based, and hybrid AM based on stock volume-based, and this stock-based manufacturing. Then hybrid AM based on waste and hybrid. So you can see the time is 7.51 hours. The time has reduced when you do the feature based, but the time has increased when you do stock based. So it's almost higher than the this 7.5 has gone up to 9.43. But the cost was, but if you look at the total time for the impeller, it was less than this. So for some parts, you can see that the total, the stock based came down very comparatively with respect to the small, this SM. So SM is 51, but you see it's 38. It's much lesser. I think almost 12 hour lesser. 12 hours, like you finish faster than 12 hours when you do, subtractive machining than hybrid. So this is kind of a very interesting insights that we get. Similarly, if you look at the cost, we are able to bring down the cost drastically because when you're doing feature based. But if you use stock based, the cost is not so drastically reduced, but the material aspects gets reduced, right? So that's the idea. So this is the buy to fly ratio comparison material efficiency, which will give us fairly a good idea. So this is what we wanted to basically understand. If you see the material efficiency of a turbine blade is only 13% in subtractive machining. It's an extremely poor percentage, right? So it's a very extremely poor percentage, 13%. An impeller, if you do subtractive machining, so that means you are going to waste a lot of material as a chip here. In hybrid AM2, it's still extremely poor for a turbine blade because still it required a lot of machining, probably. So that's the reason why the material efficiency for the turbine blade is poor. But comparatively, the impeller had excellent material efficiency in the case of a feature-based approach. But if you see the turbine blade, the reason for this is because the features are, even though they are free-form features, they are single-axis features. They are not in multiple axes. So your deposition time and deposition angles are not so complex for the impeller. So that's why you have a better material efficiency in this angle. So you have a better catchment efficiency and material efficiency. Whereas these blades are continuously rotating and the angles are continuously changing with the nozzle angle. So normally you'll have poor catchment efficiency and you will have poor material efficiency also in the case of feature-based volume partitioning. But if you look at stock-based, the efficiency is fairly good, and the material efficiency is fairly good. That means when you combine additive manufacturing and machining in one single station, these are done in one single station. It's not, you have a separate machines for 3D printing, separate additive manufacturing, separate machine, but you cannot immediately start machining it. After you build, you have to allow the part to cool for 5-6 hours. And then only you can start machining. It's a lengthy process, but I have not considered those wait times for the part to cool and stuff like this. So we started looking at only the processing times. But if you add those times where you have to wait for the next set of machining to begin before the parts cools down, it may be a little lengthier too. But those are some assumptions that we had for our analysis to better understand the material efficiency aspect in buy to fly. And if you see the buy to fly ratio in stock base is excellent, but as you see, this is very poor. This is moderately, doing well, but this is very good in the case of buy to fly ratio for impeller. Is extremely good for feature based, right? So then you have hybrid, right? So you can see that the impeller does fairly well in feature based stock partitioning and feature based volume partitioning. This is a very interesting insight that we have got. So that's the conclusion that I have about, we have two different hybrid manufacturing processes. Way to partition that we have analyzed, and economics we have analyzed. And we could see that the turbine blade, the feature-based volume partitioning was found to be more material efficient, but the stock was to be cost effective. Whereas in the impeller, the feature-based volume partitioning is material efficient, whereas the cost effective, but the stock was based leadership. Both material and cost was really good in feature-based than the cost-based. That's stock-based, right? So with this, I think these are some references that I have. Any questions if you have, I'll be able to answer. I'll stop sharing my screen now. I'll wait for any questions from the audience. Okay, so there are some questions. I think I already have a few questions to answer. So the organizers will give me some time to answer these questions. Do you have time to answer these questions?
Yes, sir. Yes, sir.
Okay, great.
Carry.
Yeah. So I think one question is there about Gopi Krishna. Sir, explain the impact of hybrid additive manufacturing and mechanical properties and what is microstructure. Okay, so anyway, this is we are talking about mostly about environmental sustainability, but I will throw some light into mechanical properties. See, mechanical properties of additive manufacturing parts suffers from three major issues. One is heterogeneity, anisotropy, and also it suffers from micro cracks and porosity. So it will be lesser. So now we have seen some studies which have come up, which we have seen the mechanical properties of AM pots are as good, as comparable as the rot pots, and then as good as sustainable manufactured pots and string. We have seen a lot of these things. But the question is, let's say when we ask a practicing engineer who was using these parts in aerospace, they already started using this in aerospace, and a few rockets have flown. Even in Indian scenario, they have done some startup companies have used. So they have found no problem with the microstructure. They were able to basically control the microstructure through in situ monitoring. They get comparable properties as that of a as wrought or as formed or as machined component. So through careful control of process parameters. So the microstructures, especially we have seen, so we have seen a lot of problems in machining titanium because of the superplasticity. We have seen a lot of problems in forming titanium because of its reactivity, especially hot forming, and also while we have considerably purging the entire environment, we are doing that in vacuum here. So we are building layer by layer. Only there is some heterogeneity issues. Functionally loaded parts should not be oriented along the build direction, but since we are continuously changing the build direction, that is also going away. In powder bed fusion, you still have the problem of heterogeneity and things. But what happens to rapid cooling heating cycles? Is the material aging? Does it have any issues there? Yes, we have a lot of issues. That's why the entire academic community, metallurgists, are working towards improving the process, and they have done a lot of good work. So now the processes are being approved by FAA for aerospace, and in India, Semiloc, which approves for DRDO and ISRO. So they have approved. And the second question by Kamesh is there any challenges faced by hybrid additive manufacturing? Okay. See, there are multiple challenges. In fact, there are multiple challenges. It will take almost another one lecture to say about all those challenges. First challenge is the process planning. So we need to have a better process planning algorithm. Second one is speed, productivity. And third one is we have lots of other challenges in terms of material being reused from the machining, aging of machines and things. And other challenges are, we have seen some of the parts undergo creep, some of the parts undergo fatigue. The fatigue strength, I think there is another one question asked about fatigue strength. So for low cycle fatigue, so it fairly does well, but for high cycle fatigue, still a lot of studies is yet to be done. People are not done with respect to titanium. So they have demonstrated some applications of dynamic loading where high cycle fatigue, involving high cycle fatigue, and they have demonstrated some very useful applications in some situations, but they have also shown some failures in some cases. Yes, after you do the net shaping, when you build a near net stock and machine it, there will be some change in the fatigue strength, especially because of the layering phenomena. But now they have gone for high temperature melting. The material is completely melted and glued to the previous layer. It's not still anymore. So that's why it is as good as any other parts. That's what you are conventionally manufacturing. So I'm not saying this thing. Okay, another question somebody asked: is there any other parameter other than buy to fly ratio governs the production cost of aerospace components? So yes, there are many parameters, but in this study we focused on two things. One is about the total time that it takes to produce, wherein we have seen many factors have come in the cost model, right? So, and we focused on material efficiency primarily from the reason that material is becoming very scarce. So there are a lot of critical materials. That some materials are there now being sourced from Russia, and we have problems in sourcing them. There are conflict materials, there are critical materials that we use, especially titanium being expensive. So, and also it is leading to material sustainability. So we need to arrest the flow of materials that goes into technosphere and reduce the wastage as chip, and reduce the material that is going, even chip when you throw them out. So they cause a lot of problems to the waterways, and then also it you might be knowing in machining there's a large community of people who are working on minimum quantity lubrications, and then having a vegetable oils as a coolant for machining. So they have so much of sustainability issues in machining, which are otherwise being taken care of in the additive manufacturing. That's the reason why we are more focused in trying to look at more from the perspective of material as a sustainability factor. Energy is another factor. In machining and all, energy may be very less. Here we are using high intensity energy sources like laser and plasma, where they have some lasers like CO2 laser has a very single digit wall plug efficiency. Like 6% is the efficiency of energy conversion from electrical to optical. Whereas fiber lasers and semiconductor lasers, they have more than 36 to 40%. But still, it's very poor compared to welding and machining, where you have 76 to 80% efficiency, right? So in energy transfer efficiency from the arc to the workpiece, right? So that's the fairly good amount of efficiency. But still, there is energy-wise, there is a lot of issue. We are still working on some of the energy. We have published few in the energy. We are still working at energy issues, cost issues, right? So those are the sustainability issues. If you are talking about production cost, if you see the production cost largely depends upon the operation cost, the machine hour rate, the energy cost, because nowadays European manufacturers who have the densely populated European manufacturers who produce aerospace components, there the energy cost is becoming a great concern for them, because energy is not cheap anymore. So because of the conflict, so they are the energy security is becoming an issue for them. So that's why they are also optimizing energy, which affects the production cost, right? So a lot of energy related, that also affects the sustainability and also the cost. So simultaneously it works on, people are working on optimizing the energy cost around the building cost models, which are based on energy and on the energy. So that another thing is the cost will be also influenced by your availability of the labor, and then the machine hour rates, and also about your ability to use materials which are going in, like for example coolants and other things. So a lot of other materials that goes into it, and water is also becoming a scarce commodity now. So people have analyzed the water energy nexuses in this manufacturing process. So those all contribute to kind of what you call as this total footprint, energy footprint of this. Yeah. So these are the questions. Okay, so there is, I think Dr. Veerappan is asking a question. So is there a possibility of surface defect after cold spraying over this hybrid air part? Okay, so these are questions, I think, which are of very much interest to the academic community. Now, I think cold spraying or any other surface modification technique that you use for aerospace components, because we know that aerospace components, some components are also for high temperature applications, some components are not for high temperature applications. Especially we know about the Brayton cycle. We know about when the temperature of the engine, temperature operates, is much higher, your efficiency of the engine is going to be higher. You'll be more sustainable if you have material which withstands higher temperature. So that's why nickel alloys, which has a maximum service temperature, are being used in engine with the coating. So they use a lot of zirconia coating. So GM stabilized zirconia and other coating that they apply to basically increase the engine temperature, so that they can achieve good accuracy, good engine efficiencies in the Brayton cycle, prop and turbojet engines, aircraft engines, and other non-thermal applications also. There is a lot of coating that people do. So here people are doing cold spraying, plasma spraying, and other techniques to basically coat these materials with sacrificing blender first, and then the zirconia coating to basically increase its temperature, maximum operating temperature. Now, surface roughness, yes, it slightly affects. But the coating industry has actually has successfully produced a lot of good coatings after machining. So I don't think the surface finish is a matter of great concern after cold spray. So it's not a big problem. But you have cold spray based additive manufacturing techniques where you have a poor surface finish where you need to improve by machining, and then you go for ceramic coatings on top of it. So about surface defects, yes. So you may have to use some NDT techniques, non-destructive testing to analyze the surface defects. People have analyzed it in the past, and they have found some defects, especially they have gas-induced porosity. In some cases, they have some small micro cracks. In some cases, due to the powder entrapments, and also some process-induced porosity they have observed, which causes micro cracks. And after coating, also they have found some cracks. So, but they have found a way to basically do heating and other things to basically close these pores and get the cracks sealed through multiple post-treatment, post heat treatment process. That's there have been a lot of studies around it. So I think it's not a question of difficulty anymore, because they have been using these parts in aerospace. So I don't think there's a big issue. So, but only thing is it adds a little bit of cost there, because you have to add one more post-processing process there. So that's what I say, when you plan, then when you plan and then prepare and print it, then you have one more step called perfecting it, where you have to perfect it. So that is what we call post-processing techniques of all these things which you need to do. So I think I answered the question. If there are unanswered questions, you can also write to me. My email ID is I'll type it here, so you can just type it. You can write it to me if you have more questions.
Participants, Spockets faculties, if you want to have clarify any doubts, you can ask. Sir is here. Professors, if you have doubt, you can ask any queries regarding that. Sir, thank you, sir. Thank you for giving us such a wonderful session on hybrid additive manufacturing. Actually, so far I didn't know about this hybrid manufacturing, and especially the buy to fly ratio. I didn't know. Today only I came to know that buy to fly ratio. That is a ratio. What you have said last 1:1:1. I thought that is very impossible to keep that ratio. But after seeing this presentation, it's very amazing to see a ratio, building ratio like that. Thank you a lot for sharing the information.
Okay, thank you. So I think thanks for the audience, for the patience listening, and also for intriguing questions. So we'll meet again when the opportunity comes in any other sessions. I thank the organizers for inviting me to this session and also arranging this very nicely. Thank you all. So thank you, Ananda.
Akshay,
Thank you so much for inspiring us in unique ways, sir. It made us ponder out of the box. It was a pleasure having you. Hope you have a great day. Thank you, sir.
Thanks for the nice words, man. Thanks.
Thank you, sir.